Good morning, folks. Today we're going to start pulling things together. We've talked about these series for a long time. Today we're going to start putting functions back into the mix so we can start doing calculus. So we, in recent times, have talked about the convergence of series, which are just a list of numerical values, right? Where these are literally just a bunch of real numbers that we're adding up. And so these series, we've now got a pretty good handle on when they converge and when they diverge. Our job today is to take this a step further and turn these into functions. And so you see where I've introduced an x here that makes it literally a function of x now. So we start by convention with the index 0 so that our lowest term is just a constant, and then we have a linear term and a squared and a cube and every single power of n that's a positive integer. So this is an infinite power series, right? So this is infinite in the sense we had before, so we've still got the question, when does this converge? But now we're going to have to answer that in terms of, well, it's going to depend on the a's, obviously, just like it did, but now it also depends on these x values. What x values are allowed for convergence? So let's just do an example and see what happens. Okay, so we're going to generalize that idea of a power series in a bit, but to begin with, let's just take a basic power series that has that form, and in this case, it's going to be 1 plus x over 3 plus x squared over 3 squared. My 3's are terrible today. X cubed over 3 squared plus x to the 4 over 3 squared, and so on. We want to know if this power series converges. And now we've got x's in there. X is an unknown. X is our variable as usual. We might have to ask for what values of x. Well, looking at that general term, in the past, this is what we would have called a sub n, right? In our previous section, this is what we would have called the a sub n term. Now, the notation the book uses confuses that a bit, so we're going to be thinking about not just a sub n, but a sub n x to the power of n. That's the general term that I'm seeing here in the power series. And so the terms that appear in this power series, this is just a sub 0, this is a sub 1x, this is a sub 2x squared, and so on. And so if we're looking at the convergence of these things, well, I'm looking at this general term and it involves an exponential, and so a good way to deal with series that involve exponentials is the ratio test. So let's use the ratio test, which means looking at the ratio of neighboring terms, right? A sub n plus 1 over a sub n in our notation in the previous section. But the thing is, we've got to look at this entire term. So we're going to compare the nth term in this power series, which is a sub n x to the n, with the n plus 1th term in the power series, which is a sub n plus 1 x to the n plus 1, right? Those are the two powers, those are the two terms in the power series that are neighboring. And so it's the ratio of those terms that we're interested in. And so coming down here, we're literally going to take a sub n plus 1 to the power of n plus 1 and divide it by the nth term, which was a sub n x to the n. So that ratio is what we're interested in the ratio test, because remember, we're literally taking the ratio of one term to the next. So don't get confused by the symbols here. The a sub n's have changed their meaning. In the previous section, we would have called this whole box a sub n. So rewriting that, what we're going to get in this case is x to the power of n plus 1 divided by 3 to the power of n plus 1. That's the n plus 1th term. And we're dividing that by the nth term, which is x to the n over 3 to the n. So I take that reciprocal. Right, the nth term is this object flipped upside down. So now we can simplify that. That's the idea here. We simplify this by cancelling the powers as much as we can. So there's an x to the n there, there's an x to the n plus 1 on top, x to the n on the bottom. That's going to leave us, well, let me just write it out. Gathering those terms so we can directly cancel them, we're going to come up with this. And then cancelling that is relatively straightforward. Let's go to the next page. And so this is what we just had on the previous page. And so we can do the cancellation here with the x's, and we're left with an x over 1, if you like. Doing the cancel, I left a plus 1. If you do the cancellation here with the 3's, you end up with 1 over 3. And so this whole limit, there's no n's left. And so that whole limit is just x over 3. Now, the ratio test says that the limit of consecutive terms for an arbitrary value of n in the limit as n goes to infinity has to be less than 1 for convergence. And so by the ratio test, this series, this power series now, converges when this quantity is less than 1. But it diverges when that quantity is bigger than 1. And we can make no conclusion at all when the absolute value of x over 3 is equal to 1. So if we think about a number line here, we've actually found a good region of convergence. Here's the x-axis, right? On this x-axis, I'm going to think about this inequality. I can rephrase this inequality as the absolute value of x is less than 3. So the absolute value of x less than 3, well, those are all the points between minus 3 and 3. And so we've seen that this power series converges for all the values of x between minus 3 and 3. We don't know what happens at 3 and minus 3 because the absolute value of x equals 3 is those points on the boundary there. But then we know it diverges when the absolute value of x is bigger than 3, right? Out here we've got a divergent power series because this is the region literally where the absolute value of x is bigger than 3. So the distance from the origin is more than 3. So we've got a region of convergence and it's centered around 0 here. And you can see we go 3 to the right and 3 to the left around that central point at 0. We still don't know what happens exactly at x equals 3 and minus 3. They're the values that are exactly 3 units away because the ratio test led to no conclusion. So let's plug into the series and try and work out what happens at those points specifically before we come back and make a conclusion. So we have two sort of possibilities to look at. The absolute value of x is equal to 3 when x equals 3 and when x equals minus 3. Let's consider each of them separately. So when x equals 3, I'm literally going to plug in that value, right? If x is 3 everywhere, then this becomes the sum from 0 to infinity of 3 to the n over 3 to the n. Well, I can simplify that one. So this is the sum from n is 0 to infinity of 1. So when n equals 0 you get 1, and when n equals 1 you get 1, and when n equals 2 you get 1, and when n equals 3 you get 1. And so you're adding 1 an infinite number of times. That must diverge, right? One way of thinking about it is as the limit as n goes to infinity of the nth term here, because we're just back to talking about the same thing as we were in the previous section, and that's why we were doing it in the previous section, so we could make sense of this stuff. The nth term is just 1. Right? So in the limit that n goes to infinity of this, we get 1, and that's not 0, so the series diverges by the divergence test. Right? The divergence test says if the limit of the sequence is not 0, then it can't possibly diverge. And that's because we're just adding a finite number an infinite number of times, so it's just got to get bigger and bigger and bigger for all time. Well, what about the other case? What about when x is equal to minus 3? In that case, this summation is going to be very similar. We're adding 0 to infinity of, in this case, minus 3 to the power of n over 3 to the power of n. And so that is just minus 1 to the power of n. Right? Because when n is an even number, this is going to be 1. And when n's an odd number, this is going to be minus 1. And so this is literally going to turn into 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. And so does that converge or diverge? Well, again, it's very straightforward. Here, the nth term, a sub n, is equal to minus 1 to the power of n. And so if we ask what's the limit as n goes to infinity of a n here, we're asking what's the limit as n goes to infinity of this alternating term, minus 1 to the n. That limit does not exist because it's just alternating forever, minus 1, positive 1, and so on. And that means that since that limit it doesn't exist, it's certainly not equal to 0, and that means the series again diverges by the divergence test. Divergence test. So there we go. We found at x equals 3 and x equals minus 3, this series diverges in both cases, and we use the divergence test to show that. And so now we can summarize what we found. So we found that this power series converges when the absolute value of x is less than 3. And it diverges when the absolute value of x is bigger than 3, that comes from the ratio test, or equal to 3, because we saw that in the divergence test. So we've now looked at every possible value of x, and we found where this power series converges and diverges. And we found that it converges between minus 3 and 3. Right? And then it diverges outside of that interval. So this is what we're going to call the interval of convergence. Right, the interval of convergence is this open-ended region -3 to 3 where the power series converges. And it diverges everywhere else. And notice that starting at the point 0, I can move 3 units to the right, or I can move 3 units to the left to describe the interval of convergence. And I'm going to call that the radius of convergence, and it's measured from the center of the power series. So a few new terms we've introduced here. We've introduced the center of the power series there, and if we measure this distance r in either direction from the center, we get this radius of convergence when we describe this interval of convergence. So 3 either direction from the center gives us that full interval of convergence. And notice how I can write that power series in this funky way, where I replace the x up the top with just an x minus 0. That obviously doesn't do anything, doesn't change anything, but this is where we see the center. If there's no number being subtracted there, then the center of the power series is just 0. In general, we might have another number there, we'll call it c. So the center of the power series we can read off from the beginning of the problem. So the radius of convergence here was measured from that center. Right? And then that gave us the interval of convergence. So the interval of convergence is always the same symbolically. Starting from the center, if I call this center C, then the interval of convergence is going to take us out to C plus R and back to C minus R. So we start with C and we add the radius and we subtract the radius. And we've got a theorem about that. So let's kind of back off from this problem and look at the general results. So following up on our example here, remember we had the series of, and I wrote it as x minus 0 to the power of n over 3 to the power of n. This series has a constant out the front, which I could write that way, x minus 0 to the power of n. So this is in general what we're going to call the a sub n, and this is in general going to be x minus c to the power of n, where c is what we call the center of the series. So in our example, the center was 0. But in general, a power series can be written like this, and it's obviously going to be a function of f. Sorry, it's obviously going to be a function of x if it converges. If it doesn't converge, it's just going to give infinite values for a given value of x, so that's not going to be very interesting. But our theorem essentially confirms that what we saw in the last example is true in general. If we have a number line, and the series is centered at C, then what this is saying, this is exactly the form I wrote down, if we're looking at this series, then it's going to have a radius of convergence. That radius of convergence might be 0, right? A radius of convergence means it only converges at the point C. Because imagine plugging in imagine calculating f of c here. This is going to be the sum from n is equal to 0 to infinity of a sub n of c minus c. Well, c minus c is 0. So this term is 0, and it appears everywhere except this first number. So everything else is going to be 0. So it's clearly always going to converge at C because the value is always just a sub 0. But away from C, it may or may not converge. So the radius of convergence is 0 if it's only converging at C, and otherwise we start at the point C and we move left and right. And the main point of this theorem is to tell us that this radius of convergence is going to sort of define the convergence. So it's going to converge in the interval from C forward a distance r and then backwards a different distance r. So one way of writing that is the interval of convergence is going to be c minus r to c plus r. Another way of saying that is the distance from the center, C, is less than r. And that's what we're saying here for the radius of convergence. So converges in that region, right? Converges when x is within a distance r of the point C, left or right, and then it diverges out here. So it diverges when that distance is bigger than r. If the radius of convergence is infinite, then it's converging everywhere on the x-axis, because you can go infinitely far to the left and the right, and the series will converge. And just to be extra clear here, this series converges absolutely. Because this is coming from the ratio test, what we're testing for is absolute convergence. Because just like in the previous example, this result is coming from the ratio test. So it converges absolutely when we're less than a distance r away from the point C, so in this region. And then it diverges when we're beyond that region. And then what happens on the boundary points, right? What happens at exactly x equals c plus r and x equals c minus r? That's what we've got to decide in particular examples. And our example will also tell us what R is. So we've still got a lot of pieces to put together here. So let's do some examples to see how they fit. All right, so let's apply this idea. We've got a power series here, x minus 2 to the power of n, divided by some multiple of n plus 1. What's the center of convergence? Right, just looking at this series, immediately we can write down the center of convergence of this series, or the center of convergence, and that's 2, right? Comparing it to the general form, comparing it to this form, we have c is equal to 2. So let's then take this and apply our tests. We want to know the radius of convergence, so we begin by using the ratio test, right? The ratio of consecutive terms in that limit is going to give us the radius of convergence every time, just like it did in the previous example. Now let's think about what's the nth term. Let me write them down here. Right, the nth term in this series is literally going to be that full thing, x minus 2 to the power of n divided by 3 lots of n plus 1. The n plus 1th term, therefore, is going to be 1 power of n higher, or 1 value of n higher. So we're going to get n plus 1 plus 1. And so there are the two terms. And what we're going to need up here, if I call this, let's call this c sub n, and this is c sub n plus 1, then the ratio that I want here is that ratio of the n plus 1th term over the nth term. So taking that limit, we're going to get these terms. And again, this is just the nth term, right? Sorry, this is just the n plus 1th term. And then the next one is the reciprocal. So this is 1 over c sub n, and this one is c sub n plus 1. And so doing that calculation, we again just cancel everything we can. And this is what will generally happen. There'll be lots of cancellation. You can see these terms. I've got n plus 1 here and n of them there. So I'm going to cancel n of them, and I'm going to be left with 1 in the numerator, one of those factors. So x minus 2 to the power of 1. And the 3's are clearly going to cancel, so I can cancel the 3's. That's nice. And then I'm left with, well, I'm not sure what to do with that yet, n plus 1 over n plus 2. So I've got a limit to take here, and I've still got n's involved, unlike last time. So continuing that calculation, we're going to get the limit as n goes to infinity. And again, you can convert to x's, and you can use the rules of, use L'Hopital's rule, or you can just do this in the Calc 1 way and divide top and bottom by n, and you end up with that. And this term here still involves an n, but this goes to 0, this goes to 0. That doesn't have any n's in it at all. And so we must be left with here just the absolute value of x minus 2. Okay? And for convergence, that has to be less than 1. And that's it. The absolute value of the power series test tells us that this series converges absolutely when x minus 2, when this limit is less than 1. And going back to our number line, we know when that happens. We've got a center at 2 here, and we're less than a distance of 1 away from that. So we're going 1 to the right, and we're going 1 to the left, because this thing can be rewritten as x minus 2 is bigger than minus 1 and less than 1. Another way of putting that is x is less than 2 plus 1, and it's bigger than 2 minus 1. So this is 2 minus 1, that's just the point 1, and this is 2 plus 1, that's the point 3. So the radius of convergence here is 1. That's how far we move away from the center point. The central point is 2. The interval of convergence, we don't quite know yet. We know that between 1 and 2, we've just definitely got convergence, right? We've got absolute convergence in there. In that interval between 1 and 3, we have absolute convergence. Because that's the inequality we come down with here, right? And we know we've got divergence when x is bigger than 3 or less than 1. So let's look at these special points, 1 and 3. When x equals 1, we don't know whether these converge or not yet, but when we plug x equals 1 in here, we're going to get 1 minus 2, which is negative 1. And so this is an alternating series, right? Minus 1 to the power of n over these terms. We need to use the alternating series test. And if you remember the alternating series test, it says to take the positive piece that's left apart from the alternating terms, And then we need to show that b sub n is greater than or equal to 0, and also that the b sub n is a decreasing sequence. And as long as those two things are true, then the alternating series converges. So in this example, a sub n is minus 1 to the power of n over 3 times n plus 1. And so the positive piece of that is just 1 over 3 times n plus 1. And that's clearly greater than or equal to 0 for all of the n's we care about, certainly, for all n greater than or equal to 0. And on top of that, notice that the b sub n is decreasing. So I'm going to write b sub n as a function of n, right? And then I'm going to think about the corresponding function of real variables, because I want to show that's decreasing. Because if f of x is decreasing, then the values that are coming out at the integer points are decreasing, and therefore the sequence is decreasing. So we've got f of x, so then f prime, the derivative of this is going to bring out a minus 1, and then we're going to increase the power to 2 in the denominator, and that's definitely less than 0 for all x that we care about, greater than or equal to 0 for all x at, where it's defined, in fact. And that means that f is a decreasing function, and if the function's decreasing and that's where we're getting the values from, then b sub n must be a positive, because we showed that up here, decreasing sequence, and that means by the alternating series test, this converges. This series converges, and that means that the power series converges at x equals 1. So that's one of our endpoints, x equals 1. What about what happens at x equals 3? Well, let's do that next. All right, our other boundary, x equals 3, we're literally plugging 3 in here. We get 1 to the n up there. 1 to the n is just 1. So this is our sum of the a sub n, and here we're going from 0 to infinity. We need to work out whether this converges or diverges, and you really should be able to look at that and say, I know that diverges, now I need to convince that annoying professor dude why it converges, right? Which means applying a test. And the best test to use here is probably the limit comparison test. Because if I think about this, we're looking at these terms, right? The reason I think it diverges is that behaves a lot like 1 over n. The sum of 1 over n diverges. That's one of our absolutely straightforward results. That's the harmonic series. It diverges. We have this, which looks a lot like 1 over n. Okay, so direct comparison test, limit comparison test, which of these should we use? This isn't a p-series. We can't do it directly. Now, if this diverges and these numbers were bigger than those numbers, then the direct comparison test would help us. The trouble is, well, if I just think about these numbers, if I made the denominator bigger, that means I made the whole number smaller. So I know that 1/3 is going to diverge. So I know that when I add these up, it's going to diverge. The trouble is, this is smaller, which tells us nothing about the divergence when I add up those terms, because they're smaller than something that goes to infinity. So this inequality is the wrong way around for the divergence test to be useful, so we should use the limit comparison test. So the idea is we're going to compare with this harmonic series, and we're going to do this comparison using the limit comparison test. Right? And it's the overall behavior of this series when n is large that makes me think about the limit comparison test. And if this troubles you, think about pulling out the first term here. So let's think about turning this into the sum from 1 to infinity of 1 over 3 lots of n plus 1. Right? I've pulled out the first term. The first term is just a sub 0. Plug n equals 0 in here and I get a third. So I can pull out that 1/3. And now what I'm going to do is compare this series from 1 to infinity with this series from 1 to infinity. Adding the third is not going to change the answer, right? The answer we're looking for here is this convergent or divergent? If this converges, adding a third is still going to leave you with a finite number. That's what converge means. Whereas if this diverges, goes off to infinity, or doesn't settle down to a fixed number at all, then this adding a third is not going to change that result either. So that 1/3 term by itself is not going to affect the result of our comparison. So I'm just going to compare with that. So the limit comparison test says take 2 series, here's our two series, and compare their terms in the limit that n goes to infinity. And these are both positive, right? And we have to have positive series for the limit comparison test to be used. So these are both positive terms for all n greater than or equal to 1. And the limit comparison test says, have a look at the limit. Right? The ratio of those two terms in the limit that n goes to infinity, and calculate that. So here's a sub n, and I'm going to divide it by b sub n. By dividing it by b sub n, this is the same as taking the reciprocal. So just avoid some writing to immediately write it down like that, but you can put it in the denominator and then rearrange fractions. So what we're left with is n over 3 lots of n plus 1, and this is the limit as n goes to infinity. Dividing top and bottom by n, I'm going to get this. Right? That's meant to be an n down there. In other words, what I'm doing here is multiplying top and bottom by 1 over n on the top and 1 over n on the bottom. Cancels on the top, leaves this factor on the bottom. This term is going to go to 0 as n tends to infinity, and so this leaves 1/3. That's bigger than 0. And that's what we needed to know. So the limit comparison test, because this is a positive number, by the limit comparison test, the series that we're interested in diverges because the one that we're comparing it to, the harmonic series, diverges also. And so we know that the power series itself diverges when x is equal to 3. Right? So this is a divergent power series. This is a divergent power series when x equals 3. It's convergent when x equals 1, and that completes our interval of convergence. So let's put all of that together. And literally what we found is that this series converges between 1 and 3. It converges also at 1. So if I'm going to draw this on the number line, between 1 and 3, we've got a convergent power series. And it's convergent everywhere in there, including at 1, but not at 3, and it diverges everywhere else. It's absolutely convergent in the middle there. It's absolutely convergent between 1 and 3. It's conditionally convergent at 1. Why is that? Haven't talked about that. It's convergent, right? We showed that. We went back here and we showed this was convergent. Look at the series though. It's minus 1 to the power of n divided by 3 times n plus 1. What's the absolute value of that look like? Well, the absolute value of that series looks like this series, which diverges. So whereas this is convergent at 1, it's not absolutely convergent because it diverged at 3, and that actually turned out to be the same series. So this is not untypical. It can be conditionally convergent at the endpoints, but it'll be absolutely convergent in the middle of that interval. So the radius of convergence here we found was 1. The center of convergence was 2, and the interval of convergence starts at the center, goes 1 either way, 1 radius either way, and then we include those two special endpoints to get the final interval of convergence. So this answers the questions at the beginning. And these calculations are quite long and involved. They use all of the pieces that we've used in earlier kind of calculations. And for a reason, right? That's why we were doing those earlier calculations. So I'm going to leave it there today. We're going to build on this in the next lecture. Hope you are well and you have a wonderful day. I'll see you later.